So here's the part nobody was expecting. We didn't just get another image of 3I Atlas. We got time. For 28 straight hours, NASA's TESS satellite kept watching this object without looking away. No snapshots, no gaps, just continuous data. And that changes everything. Because when you stop freezing moments and start watching motion, patterns appear. Brightness rises and falls. The surrounding material holds together longer than expected. The geometry stays coherent instead of collapsing into noise. This isn't a single frame you can argue over. This is behavior unfolding hour by hour. In this video, I'm not speculating, I'm not guessing, I'm walking you through what this 28-hour dataset actually shows, why it matters, and what it rules out immediately. Let's break it down. Here's what TESS did differently this time. Instead of taking a single image and moving on, it stayed locked on the same patch of sky for days. From January 15th to January 22, it captured full-frame images continuously. When you stack and align those frames, you don't get a photo, you get a timeline. Over 28 hours of usable data, this object moves cleanly across a star field while its surrounding material stays visible the entire time. That matters, because random noise doesn't persist. Background artifacts don't track motion. Processing errors don't survive hour after hour. But this does. What TESS records is a compact central source moving smoothly, with a faint but consistent extension trailing in a stable direction. The brightness doesn't spike randomly. It doesn't blink in and out. It evolves gradually. This is the key shift. Single images can mislead. They freeze geometry at one angle. They exaggerate contrast. They invite overinterpretation. But continuous observation strips all that away. With this dataset, you can now ask better questions. Does the brightness fluctuate in a repeating way? Does the surrounding material drift or stay locked to the source? Does the orientation change smoothly or snap abruptly? And the answers are already starting to show up. The light curve is coherent. The motion is smooth. The structure doesn't collapse over time. That alone rules out a whole class of explanations people were pushing just weeks ago. And this isn't a backyard setup. This is NASA using TESS, a spacecraft designed to measure tiny changes in brightness across huge areas of sky. Which means the data isn't just visually interesting, it's photometrically precise. Now here's where it gets more interesting. Because once you realize what TESS actually recorded, the next question isn't what does it look like, it's what changes when you watch it long enough. And that's where the 28-hour movie starts doing real work. This is where the long-duration data earns its keep. When you line up the TESS frames and play them as a continuous sequence, something subtle but important shows up. The brightness doesn't stay flat, and it doesn't jump randomly either. It rises and falls smoothly. That's not noise. That's structure evolving in time. You're seeing a repeating modulation in the light output, not sharp spikes, not chaotic flicker. A steady rhythm that holds together across many hours. And that immediately narrows the field. If this were a loose cloud dispersing, the signal would smear out fast. If it were a transient outburst, you see a spike and decay. If the surrounding material were breaking apart, coherence would vanish. None of that happens. Instead, the signal stays organized. The extension you see in the frames stays aligned with the motion. It doesn't detach, it doesn't fan out. It tracks the central source as if the system itself is rotating or modulating in a controlled way. That's the key idea here. Time exposes behavior that images alone can't. This is exactly why this dataset matters more than any single dramatic frame. It lets you test claims instead of arguing about them. Claims like sudden disintegration, multiple independent fragments, chaotic, short-lived activity. Those ideas don't survive 28 hours of uninterrupted watching. And remember, this isn't one telescope guessing in isolation. This time-based behavior lines up cleanly with what Hubble Space Telescope constrained about the central body's coherence and what James Webb Space Telescope revealed about sustained material release in the surrounding environment. Different instruments, different wavelengths, same underlying story. What you're seeing in the TESS movie isn't a one-off anomaly, it's continuity. And continuity is hard to fake. Now comes the critical question. If the behavior is stable over hours, what does that tell us about the source itself? That's where the implications really start to stack up. While TESS watched motion, James Webb Space Telescope looked at something else entirely: infrared. Across multiple observations in December, JWST saw a compact central source surrounded by a warm, extended cloud. That structure stays consistent from frame to frame. No sudden collapse, no breakup. Then there's the spectrum. Clear signatures show up across the mid-infrared range. Water, carbon-bearing molecules, and carbon dioxide bands are all present. More importantly, their relative strengths change over time. Water drops faster, other species linger. That tells you the surrounding material isn't static. It's being replenished and redistributed, not dumped all at once. So now we have two independent views saying the same thing. Time domain data shows stability. Infrared data shows sustained activity. Different instruments, different methods, same behavior. And when that happens, it stops being a visual curiosity and starts becoming a physical problem you have to explain. Now look at the second set of maps. These aren't images in visible light. They're spatial maps of different molecules in the surrounding cloud: water, carbon dioxide, methane. Water and carbon dioxide are tightly concentrated near the center, with smooth fall-off outward. Methane is noisier and more diffuse, but still centered on the same source. More importantly, when you compare different days, the balance changes. Water drops faster. Other components linger. That tells us the surrounding material isn't a single dump or a brief flash. It's evolving, being replenished, redistributed over time. So now we have motion from TESS and composition from JWST, pointing in the same direction. That's where the implications really start to stack up. One last check. Hubble Space Telescope isolated the central source across multiple visits by removing the surrounding glow. Each time, the result is the same: a single, compact core. No split, no disappearance. 3 instruments, 3 different methods, same underlying behavior. So the real question now isn't what this object looks like in a single image. It's what kind of interstellar source stays this coherent, this active, and this consistent across time, chemistry, and geometry. As more data comes in, we'll see whether that picture holds or finally breaks. If you want to follow this as it unfolds, subscribe. And let me know in the comments what you think the 28-hour data is really telling us. I'll see you in the next one.